All right, welcome everybody. Hope you all got a chance to vote today. If not, polls are still open, so go vote. Remember, you don't need to be pre-registered in Illinois, so as long as you have some sort of ID that has an address on it, you can just go and register to vote. So you should do that if you want to, I guess. All right. Before we get started on our new chapter, there's a question about this table and what do you do in a situation like the third row where the concentration is given not in a nice even number of 1 times 10 to the something, where you can just put that exponent in, but something like 2 times 10 to the something. What do you do with that? And the answer is you have to calculate that with a calculator, or unless you know some other way of doing that. So what I would do in this situation, since my calculator is not fancy, if you have a calculator like this, you can't do it. So you won't see something like this on a quiz or exam because we only require these kinds of calculators. But let's say you've got a slightly better calculator that does have a log key on it. So here's how you do that. You first need to type that number in. And since calculators like this aren't great with scientific notation, I would probably convert that to standard notation. So 2 times 10 to the minus 5 is 0.00002. 5 decimal places away. So then I take the log of that, switch the sign, and so the pH is 4.7, let's say. And that would be acidic. So is that what you got, but that's not what it said in the answer?
No, I just didn't know how to get the hydroxide.
Oh, so the hydroxide concentration, yeah. So the best way to do that, there's 2 ways to do that. If you have a good calculator, you can divide by 10 to the minus 14th. Or you can divide 10 to the minus 14th by whatever the hydroxide concentration is. I think the easier way to do it is to think about that pH plus pOH equals 14. So that means that if the pH is 4.7, then the pOH is going to be 9.3. But we wouldn't write that as 10 to the minus 9.3 because we don't put decimal places up in the exponent. So you have to calculate that again with the calculator. So you'd go, for this type of a calculator, you'd go negative 9.3 and then click the 10 to the button. And so it tells you it's 5.0 times 10 to the minus 10. Something like that. In like a regular graphing calculator, you could just type in 10 to the power of negative 9.3. That's how you would do it. Depends on the logic that your calculator uses, like what order they do operations in. Is that helpful? Yeah. So you won't have to do that again on quizzes or exams. You'll just have to do ones like the first 2 rows. You will see some of these on homework because you can use calculators on your homework, but the first 2 rows, right? So if the OH is 1 times 10 to the minus 6th, that means the pOH is 6, so the pH is 8. It has to be 14. pH plus pH is 14. So then the hydronium ion concentration is 1 times 10 to the minus 8th. Same thing here. We can go like that because of the pH of 3. And then the hydroxide concentration has to be 1 times 10 to the minus 11. All right, this kind of stuff will be on the quiz on Thursday. Okay. Today then we're going to start talking about nuclear chemistry. And this is a little bit of a change from what we've done so far, which is why we kind of save it to the end. So if you have the newest edition of the book, this is actually chapter 5. We're jumping back from chapter, whatever acids and bases was it 10? Yeah, 10. Back to chapter 5. The reason for that is nuclear chemistry is really weird. It's very different from all the rest of the chemistry we've been talking about the whole semester. So it doesn't really seem appropriate to do that first when we haven't even talked about regular chemistry yet. So I think it makes more sense to do what we did, talk about all the regular chemical reactions, then talk about this weird one, this weird category that's, that's different. So that's what we're going to do now. So what is nuclear chemistry? What does that mean? What does it mean to be nuclear? What are we talking about here? Anybody know anything about nuclear stuff? Have you ever heard of nuclear?
Bombs.
Like about bombs?
Yeah.
What happens in those bombs?
Deadly.
Deadly? Explosions. But like chemically, do you know what's going on in there?
Split atoms.
So they're not splitting an atom. Yeah. If we were to make kind of a general category here, nuclear chemistry is the chemistry or the changes of the nucleus, which, as you probably remember, is the protons and the neutrons. Why is that different from what we've already been talking about? What have all the other chemical reactions we've dealt with in the last few weeks involved?
Electrons.
The electrons, yeah. So most chemistry, most of the other stuff we're talking about, and the stuff we'll be talking about again next week, is all chemistry of electrons. So this is the special chapter about what's going on actually inside the nucleus. So it's very different. And we're not going to talk about any of the same kinds of things that we've been talking about. There's no bonds, there's no sharing electrons, losing electrons, all that kind of stuff doesn't really come up in these because we're talking about what's happening inside the nucleus of an atom. So that's what makes it very different. All right. So we should talk about a couple terms that come up in these types of reactions and that you've probably heard before, but maybe you don't have a really good definition of from a really specific way. And the first one is radiation. You've probably heard that word before. Radiation, maybe, possibly. Everybody's just in sort of like a staring, non-responsive mood today. That's okay. Yeah, we've heard that term, and we usually associate it with probably bad things, I would imagine, right? And that's reasonable, I think. But actually, radiation is a much more general term than that, kind of like nuclear chemistry. So radiation refers to any emission of energy and or particles. So anytime something emits energy or emits particles, like stuff comes off of it, that's known as radiation. And there's a lot of examples of that that is not harmful at all. So things like lights. Lights work via radiation because light radiates out from some source, whether it's a heated up wire or an LED or whatever it is. The light is radiating outward and it's visible light, and that's a type of radiation. Radiation of visible light is how we see things. You can also radiate particles. So an example of that is an electron beam. I don't know if anybody remembers, but long time ago, there used to be these like computers and TVs that were really big and weren't flat. Does anybody still have some of those? Maybe some around? Yeah.
Yeah.
Yeah, but you know what I'm talking about? They were like they were big and they weren't just like skinny. And the reason they were so big like that is because they had a tube inside that shot a beam of electrons. And it would shoot the beam of electrons at a screen in the front, and whatever the electrons hit would light up, and it would kind of go down like this and back up again, and that's how you got the picture on that screen. So that's a type of radiation as well. You'd have a emitter that was emitting electrons, also known as a cathode ray. but it's a beam of electrons. So most radiation is harmless, whether it's like radio waves or microwaves coming off of our cell phones or light coming off of lights, whatever. A lot of that is just harmless. It's harmless because it's low energy. It doesn't have enough energy to do anything to atoms and molecules. The subset of radiation that is a problem or can be a problem is called ionizing radiation. What do you think that is? What do you think it means for radiation to be ionizing? What do you think it means to ionize something?
Get rid of electrons.
Yeah, get rid of electrons. So make something into an ion. So ionizing radiation is radiation with enough energy to remove electrons from atoms or molecules. So this type of radiation can actually knock off electrons from things, and that's where it can start to cause problems. So when we talk about light, we talk about ultraviolet light and higher. Visible light doesn't have enough energy to remove electrons, but ultraviolet light does, and then higher energy light does too, like X-rays and gamma rays, that kind of stuff. Those are types of ionizing radiation that's just energy, just pure energy, light. There's also ionizing particles. That's a little bit what we're going to talk about today. Some of these radioactive elements release particles with enough energy that they can knock off electrons. And that's where it can cause trouble, because if you ionize stuff where ions aren't supposed to be, you create damage. An example is DNA. DNA are these big molecules in your cells. So if ionizing radiation hits DNA, it can knock an electron off of the molecule, and that destabilizes the molecule and causes it to bond in ways it's not supposed to, and that leads to things like cancer and other problems, other types of mutations, birth defects, that kind of thing. So those are the kinds of things that we have to be careful of when we think about shielding ourselves from radiation. It's really this type of a radiation that's the problem. It's not just all radiation in general. Then the other definition is that we're going to deal with in this chapter a lot is what we call radioactivity. And this is where we get these nuclear reactions, because nuclear reactions don't just happen to anything. Only certain types of elements are radioactive. And radioactivity is what happens when nuclei in the atoms nuclei, break down or somehow change and these emit radiation. And the key part here is this breakdown of the spontaneous breaking down of an atomic nucleus. That's very different from something like a light. So the way a light works, kind of like when we did the flame tests in lab, you put a bunch of energy into something, which we do from electricity in a light, and then the atoms re-release that energy back out as light. But nothing's really changed chemically. In a nuclear process or in a radioactive process, the nucleus of the atom actually breaks down. So it loses some particles or it breaks apart somehow. And in the process of that breaking out, radiation is emitted, is produced. And that's what we're going to talk about in this chapter, these different reactions that produce radiation. Oops. So before we get into that, let's review a different way to write atomic symbols that we used to do earlier in the semester. So if I write an I for iodine, and then I write a couple numbers by it. Remember seeing stuff that kind of looks like that? What do those numbers mean?
The weight and number of neutrons.
Close.
Pro-
Yeah, protons and the atomic mass or the mass number. So the bottom one is the atomic number. That's what we see on the periodic table. And that's the number of protons. And then the top one is what we call the mass number. Which is the number of protons and neutrons. And if you remember way back in that early chapter, we talked about if you look at an individual nucleus, it's going to have an integral number of protons and neutrons, meaning like a count. It's not going to be a fractional number. The reason the atomic masses on the periodic table are fractional is because it's an average of different isotopes that occur in nature. So iodine has an isotope 131, but it also has, 126 or 120. Yeah, 126 and some other ones. And the average of all of those that exist give us the number that's on the bottom. So if we're looking at a specific isotope, which we always will be in this chapter, we're going to specify it with that little number. Because we know some stuff now, we'll often not write both numbers. We can also express this with just the top number. That bottom number is redundant because if we know I, we know it's got to be 53. The atomic number goes right with that. And then if we don't want to have to worry about formatting that, a lot of times you'll see it written like this, I-131. All right, so let's look at some reactions. And we will do a lab with this too, so we'll get to see some of these particles and things. We're going to look at 3 different types of decay reactions, and then a couple, if we have time, a couple other ones. The first one is called alpha decay. Sometimes using the Greek letter alpha. And these all kind of have these weird names like this because when they were discovered, people who discovered them weren't really sure what these particles were. They didn't know if it was, they thought it was they thought it was a new, like undiscovered particle. Now we know that they're not new, they're just other things that in this situation. But at the time, they didn't know what they were, so they just named them alpha particle. We're gonna look at beta particle, gamma rays, kind of like X-rays. They didn't know what they were, so they just called them X-rays, like something rays. So an alpha decay process is when a nucleus loses an alpha particle. And an alpha particle is a particle that has 2 protons and 2 neutrons. So it's not like separately losing 2 protons and 2 neutrons in different directions. It's one particle that's made up of 2 protons and 2 neutrons. That's actually a known thing. There's an element that's made up of 2 protons and 2 neutrons. You know what it is? I figured it out. Helium, yeah. Helium has 2 protons, and a helium nucleus has 2 protons and 2 neutrons. So this is actually a helium nucleus. And so we write the alpha particle as if it were helium, like this. So that's an alpha particle. Sometimes, less commonly, you'll see it written with an alpha instead. But since we know that's a helium nucleus, we're probably going to see it the first way more often. So in an alpha decay reaction, a radioactive nucleus loses an alpha particle. And that means that something else is going to be left over. So the way we write a balanced equation for this looks something like this. Let's take uranium-238. And let's say we know that it undergoes alpha decay. So that means that one of the products of the reaction is an alpha particle. Which is like that. And then we can figure out what's left based on subtracting those numbers from what we started with. So we had 92 protons, we lost 2 protons in the alpha particle, so now we've got 90 protons left. We had a mass of 238, we lost 4 from the mass, so 2 protons, 2 neutrons, so we now have 234. And now we look up on the periodic table to figure out what that new element is, and it is thorium, Th, number 90. And that's it. That's the alpha decay reaction. So we can see here, 90 plus 2 is 92. 234 plus 4 is 238. That's all there is to it. Another alpha emitter is radon. Radon 86, or sorry, radon 220. So see if you can complete that reaction for the alpha decay of radon the same way. Draw your alpha particle and then subtract the numbers and see what the new compound is. So hopefully your subtraction skills are all polished up. So you write down the alpha particle, and then you've got 84 and 216. And we looked that up, and it is PO, polonium. That what you got? Great. All right, we can do this. This is an important reaction. I'll talk about it in a minute. But characteristics of alpha particles. They're big, not like on our scale. You can't see them, obviously. They're a tiny helium nucleus. But on the scale of really small, high-energy particles, these are big ones, which means when they hit things, they can do some damage. But also, because they're so big, they are what we call non-penetrating, or very, or very lightly penetrating. They can't get very far. Because they're so big, they end up hitting some other molecules and not making it very far away from that. So for instance, and this is something we'll see in lab, they can only make it a centimeter or so through the air. They can't make it through your skin. They hit air molecules and dissipate. So if you have you could have a giant, powerful, alpha-emitting radioactive rock right here, and as long as you didn't like get right up in it, you'd be okay because the air would block those those alpha particles from hitting you. Where this becomes a problem from a health standpoint is when alpha emitting stuff gets inside your body. Because now it doesn't have to travel through air anymore, it's right there. And radon is an example of this, which is this gas here. Radon is a naturally occurring gas, and because it's really heavy, it accumulates down low, like in basements and places like that. And if you breathe it in, then you've got this alpha emitting radioactive gas sitting down in your lungs and bombarding the most sensitive parts of your lungs and blood vessels with alpha particles. And that can cause lung cancer. So if you have a house or something, you probably maybe at some point tested it for radon, or if you have to buy a house, you have to get it tested for radon. If you don't know if you have, you should do that or ask other people in your house if they've done that. You can buy a little kit and you put it down in the basement for a few days and then you send it in and they check if there's radon down there. If there is, it's a pretty easy fix. You have to just basically put in a fan so that it vents outside to get the radon outside. But if you don't know what's there and you're living there and inhaling this radon, that's a problem. So that's alpha decay. The next one is beta decay. Oh, I should write out the words here. Again, using a Greek letter, this time beta. And as with before, in beta decay, the nucleus loses a beta particle. And just like before, when this was originally discovered, they didn't know what it was, so it was just a beta particle, something, the second one, the beta one. Now we know it's actually an electron. And so it's written as an E, -1, and 0. So we give the atomic number a -1 because it's kind of like it has a -1 charge as opposed to the proton's +1. And it has no mass. Well, electrons have mass, but their mass is so small that next to protons and neutrons, it's effectively 0. And this is kind of a weird thing because we're talking about nuclear chemistry. So we're talking about chemistry of the nucleus. Yet when a nucleus breaks down and loses a beta particle, it's losing an electron. So are there electrons in the nucleus? There are not. And yet, nucleus can shoot out a beta particle when it decays, and it can shoot out an electron. So how does that happen? It happens via this weird reaction. I guess it's not that weird, but reaction, where a neutron, which has no charge but has a mass of 1, spontaneously becomes a proton and an electron. So it kind of splits up into a proton and an electron. The math works out, right? 1 + -1 is 0, and 1 + 0 is 1. But now you've got this electron in the nucleus, and so that's going to be really destabilizing, and that's why it shoots out at high energy.
How does it randomly change?
Good question. That is, yeah, exactly. You have to ask some physicists what's going on there. It has to do with the arrangement of the subatomic particles, like the things that neutrons and protons and electrons are made up of. It's kind of beyond my knowledge. I don't know if that's something that we know or if it's not. Well, let's look in the book. Let's see if they say something about it. All right, beta decay. The formation of beta particles is the result of breakdown of a neutron into a proton and an electron. It does not say why. So I guess they don't know either. We can look it up. Go read some quantum physics and see if you can figure it out. So that means that an overall equation for beta decay, we're going to do it in the same way. One isotope that undergoes beta decay is carbon-14, which is what's used for carbon dating. We're going to start the same way. We're going to take our nucleus and then show it emitting the particle and then figure out what's left. Because we're putting a -1 down in that atomic number space, we have to ask what plus -1 equals 6. And so what plus -1 equals 6? 7, right? 7 plus -1 equals 6, or 7 minus 1. So the atomic number actually increases, and then the top doesn't change because it's 0 there. We look that up and we find that's nitrogen. The math still works the exact same way as with the alpha decay. You just make sure that the two sides equal out. But it looks a little bit weird because the atomic number is increasing. And the atomic number is increasing because a neutron, which does not contribute to the atomic number, is becoming a proton, which does contribute to the atomic number, or the overall charge of the nucleus. So the charge of the nucleus increases, and we end up with nitrogen. All right, so here, try one of those. This is a medically important isotope, phosphorus 32. Oh, here, you can do it. See if you can complete the equation for the beta decay, phosphorus 32. So we put the beta particle there, and then figure out what's left, which is sulfur. And keeping our table from before, beta particles are much, much, much smaller than the alpha particles, because instead of having 2 protons and 2 neutrons, you just have 1 electron. So tiny, tiny particle. Much more penetrating then. Let's think about what causes something to penetrate through something else at this scale. So we're talking about basically fitting through the space between the nucleus and the electrons, as well as just like the general density of how these things pack in the solid state, or whatever state you're talking about. So a large nucleus like a alpha particle is not really going to be able to fit through an atom, through the nucleus electron. I mean, it might a little bit, but it's probably just going to get hit by something, get deflected and all that. The beta particle can, because it's just a tiny electron. So it can pass through that area, which means that if it's going through some material, it's less likely to hit something right away, and it's going to get a little deeper in. So a beta emitting nucleus, those beta particles are going to be able to penetrate further. And so those are going to be more of like, we could think of it as a danger. When they're outside of our body, they could still penetrate into our organs and things like that. As we'll see when we do the tests in lab, not today, but next week. Right, next week? Yeah. We'll see that, we'll see how far those kinds of things can penetrate. And then the third one we're going to look at is called gamma decay. And in gamma decay, we don't lose any particles at all. We lose pure energy in the form of light. So no mass is lost. We're losing pure energy in the form of light, known as a gamma ray. So a gamma ray is just written as the symbol, as the Greek letter gamma, and then 0, 0, because it has no mass, no charge, it's just pure energy, it's just light. So if we lose pure energy, that means our equations are going to look a little bit different because the numbers aren't going to change. We're not losing any particles out of the nucleus when we undergo gamma decay, we're only losing energy. So these start with a material that looks a little bit different. It has a little m up in the atomic mass. And that m stands for metastable, which means only partially stable. So that means that this nucleus was formed as a result of some other process. Maybe it's one of the other decays previously, and therefore is not totally stable yet. And in order to stabilize itself, it has to just lose some energy. And it does that in the form of gamma decay. So it loses a gamma ray, and then the resulting nucleus is more stable now. But we don't see any changes in the numbers with gamma rays. This particular one, I don't know if they show it here or not. I'm trying to see if they have the equation for that specific one. Oh, yeah, there it is. Okay. So when molybdenum-99, which is radioactive, decays on its own, it undergoes beta decay. You see it shooting out that beta particle. But then the byproduct is this metastable technetium. And the technetium-99m then can decay on its own to produce these gamma rays. And this is an important radioisotope for medical diagnostic work. Because it produces pure energy and no particles, what they can do is give you some technetium-99m, put it in your body, it goes wherever it's going to go, and then it emits gamma rays. And by measuring where the gamma rays are coming from and how much gamma radiation is coming from where, they can tell where that technetium is in your body, like down to the almost cellular level, and that can give a picture of organ function and things like that. So I think so there's a picture of somebody making some. It only sticks around for a pretty short time. We'll talk about half-life on Thursday, but it's got a half-life of about 6 hours. So the radiation labs that use it actually have to make it right there. So they'll have a little machine that has that radioactive molybdenum, which breaks down into the technetium, and then they can use that for what they want to use it. Here, there's an interesting list in your book of some of the radioisotopes that are used for medicine. So this one is used in imaging, most widely used radioisotope. So they can get this into all your stuff and then see what it's doing, see what kinds of stuff is going on there. So some are actually used for, some radioisotopes are used for treatment. In that case, you want something that is going to like target and destroy a tumor, and then other ones are used for imaging, which is when you want to see something about it. The technetium-99 is used for imaging. You'll notice on the periodic table that technetium is 43, and it has this kind of outlined letters along with some of the ones on the bottom. Do you know what that means? What are the ones where the letters are just outlined, like that one? Those are the man-made elements, so they're not naturally occurring. So technetium does not occur in nature. It only occurs as a result of the radioactive or nuclear reactions that you can control and do and produce it. You'll also notice that those elements have below them, including some of the natural ones, they have an atomic mass in parentheses instead of a decimal. That's because of this issue of radioactivity. All those that have that parentheses are radioactive, which means they break down over time. So there's no way to get an accurate picture of what the average mass is around the world because they're always breaking down. So the number in parentheses, I believe, is usually the most stable isotope. So the one mass that sticks around the longest, that's what's put in those parentheses. So gamma rays are pure energy and highly penetrating. But that also means that they can kind of pass through you without causing damage a lot of the time if there's not too many of them. Because they're just so small, they're just high energy light, that there's a pretty big chance they're actually just going to go right through you without doing anything bad. And that's why that imaging works so well, is because even when that technetium is deep in your cells, it's still emitting gamma rays that are making it all the way out of your body that an exterior detection device can see. And in fact, we're getting bombarded with gamma rays from space all the time. Not like lots of them, but some are coming in from space. And when we have our Geiger counter, our radiation detector in lab next week, we'll be able to see that if you just kind of hold it out, you get some hits, you get some blips. And that's radiation coming from building materials and rocks, but also all the way from space. It's so penetrating, can make it all the way through the atmosphere, through buildings, through any of that stuff to get here. Okay, so those are the three major ones. There's another one listed in the book, positrons, and we'll skip that one. I'm not sure why, but it's not in the course objectives. And then the last thing we're going to look at is two other types of nuclear reactions, nuclear fission and nuclear fusion. Nuclear fission is what we most associate with like talking about nuclear things, and that is what we call splitting the atom. I'm going to pull up a picture from the book for this. Here's a picture and then also the equation down below of what happens in this process. You take uranium-235, which is a very specific isotope of uranium, and you shoot a neutron at it at high speed. And that creates this uranium-236, which is very unstable. And instead of just like shooting the neutron back out or undergoing alpha decay or something else, this particular nucleus happens to break apart. And there's a few different ways it can break apart. This is just one example. And it forms two also relatively large nuclei instead of just one little particle. And then it also forms three more neutrons that it ejects at high speed. And so this starts a chain reaction because those neutrons can then go find other uranium nuclei to connect with and then cause to break apart. And then those create more neutrons and so on and so forth. And that's why it ends up being a chain reaction. And so that's what you have when you have like an atomic bomb. So you have a chain reaction, a relatively small amount of uranium that is then allowed to react. And the key part of this thing is the end here, the energy. an enormous amount of energy is released as a result of this process. And that's what you can use in like a nuclear power plant, which a portion of our power comes from nuclear power plants locally, and then also something destructive like a nuclear bomb. Now, most isotopes don't do this. So this uranium-235 is really special in that it does this. And there's only a tiny, well, not tiny, but there's a relatively small amount of uranium-235 in the world. Most of the uranium in the world is 238, which is pretty stable. It is radioactive, but it's like, takes a long time for it to decay, and it doesn't do any of this stuff. So when we talk about like countries getting nuclear capabilities, that kind of thing, what that refers to is, can they separate out this uranium-235 from all the rest of the uranium? Because most uranium is not that, and that is only a tiny, tiny bit lighter than the rest of the uranium. So it takes very, very specialized equipment and capabilities to be able to separate out just that kind of uranium that you can then use to do fission and make nuclear power plants and also bombs. I'm not going to put it in the notes, but there's a picture, I think, also of how this ends up being a chain reaction. Yeah. To zoom out a little bit. Zoom out a lot. So there's kind of a picture from the book. There's our first reaction that we just had. And then it goes out from there to get more uranium, breaks that apart, then gets more and more and more. And so when you have something like a nuclear power plant, this has to be controlled. And what you do is you isolate the uranium fuel from the reaction so that those neutrons don't have as much uranium as they want to react with. They're kind of stuck not doing anything, and you can control the access to uranium, and that controls the reaction. So instead of going crazy in this chain reaction, it just creates the amount of power you want to create and then stops there. So that's a nuclear chain reaction. If you look down here, the math still works out. So you've got 92 plus 0 is 92. And then 1 plus 235 is 236, because the neutron has to go in first. And then it breaks up, and you've got 36 plus 56, which is 92. And then 91 plus 142, and then plus 3, because there's 3 neutrons, gives you the uranium-236. So you can still add up the numbers to get there on this one. And the last reaction we're going to look at nuclear fusion. So if fission is splitting the atom, what do you think fusion is? Yeah, combining, putting things together. And there are various types of reactions that fuse nuclei together. We're going to talk about just one in particular that creates a whole lot of energy, where hydrogen, an isotope of hydrogen known as hydrogen-3 or tritium, is reacted with itself. Tritium is a pretty common isotope of hydrogen. It's used in things like luminous watches, like military might use. They'll have these little tubes that have tritium inside, and that way they'll always glow no matter if they've been exposed to light or if there's no batteries or anything like that. It just glows because of the tritium. Also, exit signs sometimes have this in there because it allows the exit sign to glow without having any energy provided to it, like in a blackout. Should also note, though, when we talk about radioactive stuff glowing, it's not the radiation itself that glows. These particles don't produce light. They produce the particles. What you can do is you can put some other material in front of it or around it that does glow when this energy hits it. And that's why we think of radioactive stuff as like glowing. So things that like, well, science, for instance, it's not that tritium, which is a gas, is actually glowing, but it's hitting the screen, that the screen is making the letters of exit, and that's what glows. So anyway, you can take 2 of these tritium nuclei, and you can combine them to make a helium nucleus, and 2 neutrons. I think I need, wait. Let me check this, because that doesn't work out. Oh, I'm sorry, a tritium with a deuterium. That looks better. And again, you get an enormous amount of energy when those two things are combined. So nuclear fusion is great because, well, that's how the sun works, and the sun is good. I like the sun. I don't know. You guys like the sun? It's good that it's there anyway. Like, I'm glad it's not there. It also creates no hazardous nuclear waste like fission does. The products are just helium and a neutron, not radioactive stuff, and it creates an enormous amount of energy. So why don't we just power everything on nice, clean fusion energy? Anybody know what the problem is? So in order to get this to start, remember we talked about activation energy? In order to get this to start, you need about 100 million degrees C, which is really hot. So the amount of energy that it takes to actually get this reaction started makes the reaction itself inefficient, because to try to keep something at 100 million degrees is really hard to do. It takes a lot of energy. So we haven't yet figured out a way to do that. There is one way to nicely do this, and this is just to let the sun do it and then take its energy. So solar energy is really a type of fusion energy because the sun is undergoing fusion reactions, emitting that energy as light, which we can then capture and use. So that's one way. It's less efficient, but I mean, it's more efficient than doing this, but it doesn't give us quite as much energy as if we could actually like make a mini sun and just power stuff off of that, which would be kind of cool. So one of these big kind of like future goal discoveries is something called cold fusion. You heard that phrase before, cold fusion? And that's what this refers to. The ability to do a reaction like this at lower temperature is called cold fusion. And it can't really be done. It doesn't really work, at least not yet. If you look around the internet, there are various shady places that will assure you that it has been done and that the government is just keeping it secret from us. But I don't think that's right, probably, because you probably know. There are some pretty good reasons why you can't do it at lower temperatures. But hey, maybe we'll figure it out one day. Who knows? Okay, so in the homework, you will see things like what you can expect, sorry, almost there, on a quiz or exam. So we'll have a quiz on Thursday, but that'll be on acid-base stuff, not this, but these kinds of things. And in most cases, you should be able to complete the equation, even if you don't know what kind of equation it is. So we looked at those three, but let's look at some that don't really fit in those categories, which are some of these bombardment reactions, where stuff just kind of crashes into each other and makes new stuff. That's how we make new elements, by the way, how that bottom row starts to get populated, which now it's all the way full. We got to update our periodic tables. We've discovered all the elements. That's how we discover them, is we just smash stuff together until it sticks, and that's a new element. So something like that first one, A, how would you solve that? What do you think the product is there? That doesn't fit in nicely into one of those categories, but we should still be able to figure it out based on what we know about nuclear reactions. So what do you think?
10 for beryllium.
Right. So with all of these, you're just going to make sure that the numbers work out on each side. And that's really all there is to it. So 9 plus 1 is 10. 0 plus 4 is 4. And then we look up to see what that is, and that's still beryllium. So B. See if you can fill in the rest of those three. This last one there, that's going to be 53, 132. And that's iodine. See how that works? So remember, all the numbers have to work out. So 1 and 31 is 132. 0 and 52 is 52. But then over here, we've got a minus 1 down here. So that has to be 53. And this has to be 132. Next one, again, we add them up. So we've got 28 on top and 13 on the bottom. Since there's a 1 over here, we got to have then 27 and 13. And that is aluminum. And the last one, 4 and 14 is 18. So this one's got to be 17 because 17 plus 1 is 18. 2 and 7 is 9. So this should be 8 because 8 plus 1 is 9. And that's oxygen. All right, so that's how you do those. For all these reactions, all you got to do is just watch the numbers and make sure the numbers work out on both sides. And then you're good. Questions about those reactions? Okay. On Thursday, we'll have the quiz, and then we'll go over measuring radiation, half-life calculations, that kind of stuff. Okay, with the rest